I'm Sam. I'm a software engineer at YLD. We're a consultancy specializing in React and Node.js. And we're hiring. So if you want a job, tweet me. Might be able to get you one. And I'm going to be talking about React Fiber and specifically the magic in the web of it. So I'm going to be seeking definitions. Definitions of words that echo like mystical incantations through GitHub and Twitter, if you've been following these conversations, but whose precise meaning was, for me, for a long time, quite unclear. So I'm going to try and demystify these words and share some questions I have about how exactly they relate to implementations in React. I'm not going to have time to get too deep into those implementations. I'm just going to raise these questions, and hopefully we can discuss it over drinks later. So these are the words I'm going to be looking at, except I'm going to dispense with threads because we don't have time and no one likes them. And I'm going to start with continuations. OK, so I first saw the term continuations in this React Basic repo. Put your hands up if you're familiar with this repo. OK, it's really interesting. I recommend you check it out. It's Seb Markbages, one of the core maintainers of React. It's his attempt to come up with a conceptual model of what makes React special. So there's a series of concepts in there that he sees as being key to React. And one of those is continuations. So what are continuations in this context? Well, if we look at the example, we've got a component, fancy user list, which is rendering a child user list. But instead of calling that child, it's just binding some arguments to it. And we then have some code somewhere else in our application, we don't know exactly where, that's responsible for actually calling and rendering that child. So in this context, a continuation means a partial application. Here's the first of my questions. What does this represent in real React? To me, it looks a bit like when you have a higher order component and you apply some props to it, and then you sort of finish applying the rest of the props when you actually render that component. But I think there's room for interpretation. Here's a very different instance of the term continuation. So this is from a recent pull request to the scheduler for React Fiber, where continuation, I think, maybe significantly in scare quotes, is labeled as a callback that is scheduled when yielding execution. And we get an example of what is meant. So we have a function perform work, whose job is to run tasks on a queue until some deadline expires, at which point this same function is returned so that we can continue processing those tasks at some point in the future. But we also find this, which is a rather different thing going on here, but also called a continuation. So this is from a package called React Call Return, which has actually been deleted now, but it's still there in the repo. It used to be called React coroutine, and we'll get onto why the name was changed. For now, the key point is just that the continuation here is an actual React component, and it's being returned from another component for rendering at some later date. Oh, connection lost. Right. OK, so you may have seen this. Put your hands up if you've seen this. Again, recommend you check this out. This is a proposal by Seb Markbage for a new language feature, which he thinks could be useful for React, and that's for delimited continuations with effect handlers. And the meaning of the term continuations in this context is much more computer sciencey and precise, so I'm going to try and elaborate that now. So a continuation is a control flow primitive. It's in the same category of things as if-else or while. Oh, sorry, my controller's broken. Let me try and restart this. OK. And function invocation. And these are all things that help us not write code in the order it was executed. I mean, imagine if you had to do that. It would be a complete nightmare. So the way a continuation is sometimes defined is that it's the rest of the computation at a certain point. I find this definition rather confusing because I think, well, we already have an abstraction to represent that. It's called the call stack. So the call stack is a sequence of computation It's effectively a job queue, except the key distinguishing feature of the call stack is that the order of jobs to be executed is defined by the position of those jobs in memory. So it's an ordered sequence of call frames in memory. And that makes it very efficient. Because it's ordered, we know exactly where we need to be to access the variables that we need at any particular point. And when we finished executing a function, we just pop it off the call stack, so there's no need for special garbage collection. But the problem with the stack is that we can't change the order of execution once it's established, because it's built into that physical location of memory. What if, instead of storing our call frames on a stack, we stored them on a heap, and we structured them using a linked list? So we store them at random locations in memory, but we encapsulate the order between them by inserting a pointer in each one to another one. The benefit of linked lists over stacks is that insertion of new items into the list is very easy. So we can then do some interesting stuff. So here we have, imagine this is a function calling another function, which is generating a second call frame. And imagine that in this second call frame, we have this thing that we're going to call a continuation, which is just a pointer to that previous call frame. And there's a certain low-level understanding of the term where this is all it is. It's just a mechanism so that when we call return from that second function, we can use this continuation to return back to the call frame that we were executing before. And we can go on nesting like this. But let's backtrack a minute. And let's suppose that we wanted to exploit that enhanced flexibility of linked lists when it comes to ordering and insertion. So when we say a language has continuations, we usually mean that it gives us access to continuations as a first-class object. And in turn, that gives us the ability to circumvent the linear ordering of the call stack. So we call that to another function, we have a continuation, but now we have the ability to somehow take a sort of snapshot of it and have access to it in our code. We can then pass it down into other functions, or we can store it in a global variable. And we can use it at any point to return to that first call frame and skip whatever other computation might have been scheduled in between. So in languages that support continuations, the most basic functionality is usually provided under a function called callcc, which would look like this in fictional JavaScript. You call it, and you get the current continuation at that point passed into the callback for callcc, and then you can then do whatever you like with it. In this case, first time, well, when we run this code, we're going to log undefined. We're then going to get to the continuation, which we pass hello. And at that point, we jump back to where callcc was invoked, and callcc evaluates to whatever you pass into that continuation. So when we get to, we're then going to run that continuation, get to console log again, log hello, and just keep on doing that in an infinite loop because we call it again. Now, if a fiber, this is pretty much how I see the React fiber using these things called continuations. We have some work which has to be done. That work spawns some new work, but because React fiber has re-implemented the call stack, it can insert a continuation in that new work, which will allow it to return to finishing whatever was originally started. But because this continuation can be invoked in any way, we can just push this onto a queue, and we can do our fancy scheduling and prioritization and execute it anytime we want. Now, a question I have about this is, if a fiber corresponds to a component, at which points during the reconciliation and render cycle of that component can we save and restore a continuation? Well, this is a genuine question. Basically, my question is, what exactly is resumable and what not? Okay, so that's continuations. What about the delimited in the delimited continuations proposal? So far I've been describing undelimited continuations. And that's a continuation that captures the whole sequence of frames up to that point. In other words, if you call that continuation, when it exits, the program is over. In other words, undelimited continuations don't return. They're very like callbacks in the way that they work, and they have the same problems. So when we're in a continuation, the only way to get back to some other frame is to call another continuation. And if we want to process the result of a continuation, we have to do it inside another continuation. The short of it is that continuations are not composable, unless we have delimited continuations. So with delimited continuations, we only capture a certain portion of the call stack. And when that continuation has finished running that portion of the stack, it can return something. So we have some code executing normally on the stack. At some point, we mark a delimitation. We can then do fancy stuff, saving continuations, running them. But when they're finished running, we're just going to return to executing normally on the stack. So the most common operators for delimited continuations are shift and reset. And they work like this. Reset marks a delimitation. So after calling reset, at any point then, you can save a continuation. And that continuation will save the sequence of computation back to the point at which you called reset. When we call shift, a couple of things happen. The first thing is that we clear the current continuation. So that plus world, it's not run. Instead, we take that and we bind it to this cont variable. And we can then manipulate that as we like inside the body of our shift. And we're going to get a result back from it that's returned. Whatever shift returns, because that first continuation was cleared, is what reset returns. This is I find this kind of mind-bending, but it's called shift because basically it shifts the code that was inside reset into shift. So why do we like these? Well, because that continuation returns, we can compose it. And we can do stuff like this. So imagine that we have a function which takes a callback, get user ID. We can just pass that directly to shift. Shift will pass in the continuation as the callback. And whenever that callback gets called, we'll carry on executing this function. And we've done a transformation very similar to what async await and generators allow us to do. And that's not a coincidence because reset and shift are in fact very closely related to generators. So let's have a look at that now. Yield is sometimes called a mainstream delimited continuation. And I think the easiest way to see why is to implement a generator in terms of shift and reset. So this is going to be the API for our generator. We're just going to pass the body of the generator into this function generator. It's going to receive yield, which we can use to pause execution. And if we want to resume execution, we can call next. So we know that when we start executing our generator, we want to be able to save a continuation that's going to run back up to that point. So inside next, we call reset. And inside reset, we just run here whatever function was passed into our generator function. And we pass into that function yield. And yield is a function that does very little beyond call shift. So it calls shift, it takes the current continuation at that point, it stores it in resume generator, and it returns whatever was passed into yield. Whatever shift returns is what reset returns. So whatever was passed into yield is what we ultimately get back, returned from our call to next. When we call next again, our resume generator has been overwritten with that saved continuation. So we just resume the execution of the function at that point. So you can see that yield is just a very thin wrapper, placing some restrictions on how shift is used. There is a big difference in JavaScript, though. And that's that shift is deep while yield and await is shallow. Okay, what do I mean by that? Well, in a generator in JavaScript, you can only call yield within the body of the generator. If you call another function within that generator, you can't call yield inside that function, unless that function is itself a generator. That's not the case with shift and reset. So you can call shift at any depth. And that consideration will get you part of the way, but not all the way towards answering the following question, which is, why were generators inadequate for implementing React Fiber? Okay, now let's have a look at the big one, algebraic effects. So this is what that proposal ultimately is for. Algebraic effects are just a refinement of shift and reset. So here's shift and reset. Remember that what it does is clear that current continuation and bind it to that. The thing here, though, is that we're deciding what to do with that continuation immediately after we call shift. It's a bit like if we threw an error and did this. So when we throw an error, we also clear the current continuation. But we don't handle it in the same place. Okay, it's much nicer if we can handle it somewhere else. So if we take shift and reset and we apply the same sort of refinement, we can just pass a handler, and when we call shift, we're going to jump to that handler and deal with the continuation there. Because we're no longer in scope, we also need the ability to pass data into that handler. And let's just rename shift and reset handle and effect. And let's pass in the effect because we want to be able to nest handlers, and we want specific effects to invoke specific handlers. So what algebraic effects gives you is the power to construct custom delimited continuation operators. So we can extract a little bit of functionality, a set way of handling that continuation. We can put it inside a handler, and then we can use our effect similar to how we would use shift, but we've encapsulated that little bit of behavior. Here, the behavior that I'm encapsulating is just that very simple async await behavior that I showed you earlier. But the point is that we can encapsulate any kind of behavior. So we could have a much more specific handler. We would still come out with this sort of nicely composable code, but with less generic functions. So this is I find this a nice comparison. That extra structuration that you get with effect handlers is similar to the extra structuration that you get with while compared to goTo. And algebraic effects is another of those core concepts in the React Basic repo. And the example used to illustrate it was fetching context. So the idea was that you could raise an effect, you would then have a handler down here that was responsible for actually getting the value from context, and then you would call the continuation to pass that back to the original component. This idea was abandoned. So this is the RFC to the new context API, where it said that this idea was abandoned to do with issues with memoization. Also, at one point, there was a pull request with this, algebraic effects, in the actual React source code. And the idea was that since React is implementing custom error handling with error boundaries and has a form of resumable exception, why not generalize that error handling so that we can throw different kinds of stuff and handle them differently? Well, sadly, this too went, but for one crucial exception, which was React suspense. So React suspense uses this kind of mechanism. It throws a promise that is then handled, and when it resolves, the computation resumes. But we don't have any kind of generic algebraic effects in React yet. Why were they semi-abandoned? Why don't we have them? Okay, React suspense will trick you into learning about coroutines. I thought it was about algebraic effects. So how can it be about coroutines as well? And that's because both algebraic effects and coroutines are really just different forms of delimited continuations. So let's have a look at coroutines. It's an incredibly overloaded term. There are very many different definitions of it. In languages that aren't JavaScript, you sometimes find these definitions, so for example, some languages have generators that you can't pass values into, or generators from which you cannot call other generators. In JavaScript, you can do both of those things, so we don't tend to think of those as coroutines, we just call them generators. Usually in JavaScript, when people say coroutines, they mean this, which is basically async await. But there's another meaning of the term, which I think is the one more relevant to React Fiber, and that is that, as opposed to generators, coroutines can yield with a deep continuation. So it's like you could call yield at any depth of call within that coroutine. Similarly, with suspense, you can pause reconciliation at any depth and resume it. But hang on a minute. Don't we call them fibers, not coroutines? What's a fiber? A fiber is often exactly the same thing as a coroutine. People sometimes use them interchangeably. There is sometimes a difference, though, and I think it is important for React, and that's that a fiber is a coroutine that is operated using a scheduler. So we have a scheduler in React Fiber. And I think that goes some way to explaining why coroutines don't really feature, they're not really named in the React code base, apart from one very specific feature. There was some code in React Fiber explicitly labeled as a coroutine implementation. And it's not just generic Fiber scheduling code, it's a specific feature. And like suspense, it was an API giving the user some control over how continuations were created and managed. And I'm guessing it's that element of manual control that was the reason this was called coroutines. What was it? It's now called React Call Return, and as I said, it was deleted because it was too unstable, but it's going to be back, I think, from what I understand. The idea of it was that instead of just rendering a child, let me tell you the use case first. The main use case, or the most obvious one, was for layout. So often when you're doing layout, the children need to be rendered before they can be laid out by the parents. And at the moment, the only way you can do that is by rendering twice or by doing some other kind of funny business. But if you had a coroutine, you could yield execution to that child. The child could do some work to get the value that you needed in the parent, return it to the parent could then resume, and that's what this was supposed to do. It used to be called React coroutine create coroutine and create yield, and it was renamed. It's a little complicated to see what's going on here, so I've just sort of simplified it. What happens is that with create call, you pause the parent and you mark that fiber as unfinished, but you move on to processing the children. You then do something in the children to get an intermediate result. You then resume the parent in the handler with that intermediate result. And you also pass in a continuation component. And you render that continuation component with whatever extra data you have based on that intermediate result. Okay, as I mentioned, it was renamed. It's no longer called coroutine. And I'm not going to get too far into this. Suffice it to say that it turned out to be very difficult to preserve all of the state that was necessary for resumption in some circumstances. And also, I don't really know. I think it's an open question. So, thanks for listening. I really genuinely hope you can help me with these questions. These are serious questions. I'm going to try and write a blog post to answer some of them. But yeah, grab me after if you've got any ideas, or tweet at me. Follow me on Twitter if you want to read the blog post when I manage to figure out the answers. Thank you.